Hello again. This is Math 2115 coming at you from the College DuPage. The title of this lecture is Midterm Solutions, and I encourage you to be an active learner as we go through this video. By way of introduction, the first step in grading the midterm is making a key. So I've done that, and now I'm sharing the key immediately because that enables learning. Which is the main goal. So please carefully watch this video, comparing it to the work you did and saved from the midterm. Just a copy of what you faxed in as your PDF would be just fine. And to get an immediate idea of how you did. And I will be sharing numbers from my calculations on your exam soon and give you individual updates as to where you're going into midterm. Rubric is there were 10 numbered equally weighted problems. 10 times 10 is 100. And again, review your work. You did save your work, I hope, and get an immediate idea of how you did. I'll be providing numbers for you soon, and also I'm looking forward to providing you additional content lectures. Problem number 1, we were considering a set which is capital A equal A, B, C, and D, and capital B, which is the set 1, 2, and 3. And for the function parts of this, I want you to consider A, the domain. So I ask, how many relations are there from A to B? Well, a relation, as you know, is a subset of the Cartesian product A cross B. And if you take a set that has 4 elements and a set B that has 3 elements, there will be 12 elements in the Cartesian product. But each element in there, each ordered pair, can either be in or out of the relation. So it's 2 times 2 times 2 and so on and so forth. So does 2 to the 12th or 4, 0, 6, 9. Number B asks, how many functions are there from A into B? Now that means that A is the domain because I told you that. And so we're saying functions, and a function, of course, every element in A is mapped to one element in B. Well, each element in the domain is mapped to one element in the range. So A can be mapped to 3 different things in B. So can B be mapped to 3. 3 for C and 3 for D. That is 3 to the 4th is 81 different functions are possible. How many functions are there from A to B that are onto B? This might have been the hardest one of these subparts. Onto means that every element in B has a pre-image in A. So consider first, as a small example, leaving out the A. And that means that we have left B, C, and D. Now this is exactly the number of elements that are in set B. And so in this case, there are 3 ways to map the B. There are 3 ways to map the C. And there are 3 ways to map the B. But we wanted this to be onto, so I can't reuse this. So now I have 2 ways to map the C, and then I have 1 way to map the D. So it's 3 times 2 times 1. So in this case, there are 3 factorial different functions onto B. Now, this would be true for any subset with cardinality of 3, not just the B, C, and D. And since there are 4 ways for us to pick the letter to leave out, we would have a total of 4 times 3 factorial, and 3 factorial is 6 ways thus far to complete the task. But you see, this was not talking about where A gets mapped. So we can map the left out number in each time to one of the 3 possibilities. Thus we would have 3 times 4 times 3 factorial, or 72 functions possible. D, how many functions are there from A to B that are 1 to 1? Well, this set has 4 elements in it. This set has 3 elements in it. So the only way you can have a 1-to-1 function is if the domain and range have the same number of elements. They do not, so the answer is none. Number 2, let C be this set and D be this set. We're to prove or disprove each of the following statement. And it turns out that part A is true and part B is false. So let's look at my proof of this. So we're going to pick something in C and show that it must be in D. So we're going to pick a number in 1, an element of C. Now that means by the definition that in 1 is equal to 6 R sub 1, minus 5 for some r sub 1, an element of the integers. But if we look at this and we say, well, n1 then is equal to 6r1 minus 5, but that's the same thing. This is just algebra. If I distribute, I'd have 6r1. This would be minus 6 plus 1 is minus 5. So this is another way to represent n1. And if we take s, the integer here we're talking about, to be this part, then we see that 3 times this part plus 1 works, and that is an integer. And so we know that n1 is also in D. So we picked something in C and showed it was in D. So we have proven that. Part B is false because we're going to take an example, and in D we're going to say, all right, let's let s equal 1 here. And 1 certainly is an integer. And 1 plus 3 is 4. So if we take s to be 1, that makes 4 an element of D. But if we try to solve 4 minus 6r minus 5, solve it for r, we're going to get 3 over 2, and that's not an integer solution. That means that 4 is not an element of C. Number 3, in a certain state, all license plates consist of 4 to 6 symbols. So you see each license plate can have 4 numbers, it can have 5 numbers, or it can have 6 numbers, chosen from the 26 uppercase letters of the Roman alphabet, together with the 10 digits 0 up through 9. So how many license plates are possible if repetition of symbols is allowed? Well, you can have 4, you can have 5, and you can have 6. And repetition is allowed, so this is going to be 36 to the 4th power, which is this number. This is going to be 36 to the 5th, which is this number. And this one here is going to be 36 to the 6th, which is this number. These are disjoint sets, so you add them and you get this number as the sum. This is the answer to A. This is the number you should have had. Okay, part B. How many license plates do not contain any repeated symbols? Well, again, we got 4, 5, and 6. But here what we do is we have 36 ways to pick the first symbol, but then we have only 35 ways to pick the second symbol, and 34 and 33, giving us this number. When we go here, we go 36, 35, 34, 33, and 32. We get this number. When we go to 5, we go from 36 all the way down to 31, and we get this number. We add the two numbers, and this is your answer from answer to B. Now, question C asks, how many license plates have at least one repeated number, or repeated symbol, excuse me. So here's what we're saying is we take the big number, this one, minus the smaller number. You see, these were the ones that had repeated. These were the total. So the difference between the two is going to have how many that have at least one repeated symbol. And then part D asks, what is the probability that a license plate chosen at random has at least one repeated symbol? Well, that's going to be the answer to C, how many have at least one repeated symbol, divided by the answer in A. What are the total number of possibilities that can happen? And you do that division, so you're taking this number and dividing it by that number, and you get 0.352 and so on and so forth. So that is your answer to D. Number 4, you were supposed to construct a truth table for the following argument. Here's the argument, and the argument is has 3 hypotheses and then the conclusion. So does P and Q imply not R? P or not Q? Not Q implies P, therefore not R. And so you want to find the final truth column in this argument, and I'll show you the truth table in a minute. Is this a valid argument? And the answer is this is not a valid argument. And so here's what we do. We do the truth table, and we realize that what we do, the final truth column is we take the if of the and parts that are above the place where we put those 3 dots, the therefore. So if all of those things, the conjunction and of those things is the if part, and then in column F. So we say if this and this and this, then what happens here? And so we build the truth table, and we don't get all T's. We have an F there. That means it's an invalid argument. The Venn diagram problem. They call these survey problems. I like these problems. Wouldn't be surprised if you found one of these on the final exam. A college conducted a survey to explore the academic interests and achievements of its students. It asked the students to place checks beside the number of all statements that applied that were true. And so you could be on the dean's list. I called that DL. You could be in a club. I called that C. And you can be a dual major. Okay, or I guess I should say a multiple major, but I called it dual major here. Okay, so anyway, I worked through these facts and created this as the Venn diagram. And part A asks, how many students checked at least one of the statements? Well, those are the people that are in the union of these three sets. I add up those numbers, I get 55. Now there are students who, clearly because they interviewed 100, I think, out of a sample of 100 students, so 55 are inside, there's 45 outside. 55 was the answer to A, 45 is the answer to B. Number 6, which of the sets are equal? And your answer should include all of the sets that are equal. So you see, it would have been possible for set A and E to be equal, and maybe C and D, and B wasn't equal to any of them. So, you know, basically there are 10 problems right here. Each one is worth 2 getting it right. Okay, so let's talk about this. If we talk about the set of T such that T is a solution of x squared minus 6x plus 8 equals 0, you factor this. This is x minus 2 times x minus 4. That means that 2 and 4 are the answers to this. So 2 and 4 are in this set. V, it's all the real numbers between 2 and 3. That's an infinite set. This set only has 2 in it, so that's not equal. We go down here. The 4 is repeated, but it doesn't matter if you repeat a number or not in a set. The set is 4, 2, and 5. That has 3 numbers in it. This has only 2, so that's not equal to here. D is 4, 5, 7, and 2, but you're taking the difference, the set difference between that and 5, 7, so this only has 4, 2 left. So that is equal to A. And then E is the set of Q, where Q is either the number of sides of a rectangle, which is 4, or the number of digits in any integer between 11 and 99. Well, we're talking about integers here, so each of those has 2. So this is 2, this is 4. So the answer to this is A, D, and E. Now we have some calculations. This will go pretty fast. Evaluate the following permutation function. You want to know the definition of the permutation function, and when you do this, you're going to get 8 times 7 times 6, and that's going to be 3, 3, 6. Number 8, evaluate the following floor function. The floor function comes up a lot in computer science, and you knew it was the floor because you had the little feet here at the bottom, but also you knew because I told you that. And pi is 3.14, and that represents the circumference of any circle to its diameter. Actually, it's not 3.14, it's rounded off 3.14. It never terminates, never repeats. It is an irrational number. Okay, and we do have a minus sign here too. Okay, so what happens is this is the greatest integer less than or equal to minus pi over 3. So if you do the calculation, pi divided by 3, you'll get this number. And if you think about the minus sign in front, this is minus 1.04. And the greatest integer on the number line that is less than or equal to minus 1.04 and so on and so forth is minus 2. So the answer to this one is minus 2. The answer to this one is 336. Number 9, we're to evaluate the ceiling function. That means we do this calculation and then we round up. And the reason we know it's a ceiling function is we have those little feet that are at the top. And I also told you it was the ceiling function. And E is the irrational number named after Euler. So that is 2.71 and change. It just keeps going and going and going. But if I multiply 5 times that, what I'm going to do is I'm going to get 13.59 and so on and so forth. But then if I divide this by 12, I get something just a little bit bigger than, that was the numerator. If I divide that by 12, I get something just a little bit bigger than 1. So I would round that to 2. And so in your notes, cross this out because I didn't finish the calculation, but you do get 2 here. So the answer to this is 2, and that's how I'll grade the midterm. Number 10, this is the combination function, 18 choose 7. You know the formula for this, and you get 31,824. In closing, now more than ever, time is precious. Each day must count. Do the math. It will make you strong. And now more than ever, take care of yourself and of each other. May God bless you all.